In this lesson, we're going to learn about Dalton's law of partial pressures. You might actually recognize Dalton's name from the atomic theory we learned about some time ago. This is a little bit unrelated to that, but it still has an important influence on how we approached and learned about gases some years ago. So let's say we have a mixture of gases here. First of all, we have a 5.0 liter container and has an inert gas, the word inert referring to non-reactive. Has inert gas H2, and it's held at 20 degrees Celsius. In this container, it has 2.9 atmospheres of pressure of this H2 gas. Second container has 5 liters also, and it has another inert gas, helium. That's a noble gas, so we know that's usually typically unreactive anyway. And that's held at 20 degrees Celsius, which has a pressure of 7.2 atmospheres. Now, if the two gases are actually combined into one container, into another 5.0 liter container, so again, both these mixed into one, what's the resulting pressure inside of the container? So this is a question where a couple of different avenues of potential ideas come around, and let's see which ones are the ones that are most valid. First of all, the question should be asked, the hydrogen molecules, do they interact or do they interfere with the helium atoms? And that's the main thing. So do the two of them somehow affect each other so that they don't, you just kind of have their own independent pressure? Well, it turns out, yeah, they actually don't. So it turns out they don't interfere with each other in any way. They're very much independent. And why is that? Well, don't forget that they're not going to react with each other because they're both inert, right? They're not going to exchange electrons or do any bonding. And also, the two of them, well, they kind of just occupy different spaces. So they both again, are all in there, but they're not really stacked on top of each other. They're not really attracted to each other, not doing anything to each other. And so they're very much independent. So they both exert their own pressure, and therefore the resulting pressure is actually just the sum. And that's kind of what this slide right here is showing. So let's kind of break this down. First of all, on the left side, you have two of these two of these little pistons here. This piston right here, there's like a little disc on top of it. It's being held down by these two weights. And then here you have all the little H2 in there. Turns out there's 0.6 moles of H2 in there. And that's not super important, but the idea is that this does have 2.9 atmospheres of pressure. Then you have this other container on the right side. Again, once more, you have 7.2 atmospheres of pressure of helium this time. And you can see all the little dots of these are little spheres bouncing around and so on and so forth. And then you have these individual weights on top of it. So there's 5 weights on this right side. There's only 2 on this left side. So if you put the two and put them in the same container, right? We're not talking about doubling the volume. We're just talking about putting the two into another 5 liter container, the same volume, keeping it constant. The total pressure is just the sum of the two, right? So you have 2.9 plus 7.2 makes 10.1 atmospheres. And you see all the individual particles floating around here, and they're basically, again, doing their own thing and completely independently. They're not bouncing into each other. That affects their pathway in any way. They're just both in there almost as if they're just side by side, independently living and not really interacting. And that's effectively what the Dalton's law of partial pressures is about. For any mixture of gases in a container, the total pressure is the sum of the individual pressures that each gas would exert if it were alone. So in a mixture of gases, you kind of use a little expression of P total. Sometimes we use P and then lowercase, or at least a subscripted T there. Is equal to P1 plus P2 plus P3. And the 1, 2, and 3, of course, relate to whatever gases you have. Those can change depending on the density. So if you have P of H2 or so on and so forth, like we saw in the previous one, I'm going to also write it like this, P of H2 plus P of HE to get the total pressure. This next term right here is the partial pressure. And this is something that is also a little confusing at first, but the partial pressure really just refers to the pressure of a part of the gases, specifically related to a single substance. So the fact that the H2 earlier had 2.9 atm and the helium had a pressure of 7.2 atm, you'd also then describe it as the partial pressure of H2 is 2.9 atmospheres, and the partial pressure of helium is 7.2 atmospheres. So when they ask you for the partial pressure, it's just asking you for the pressure of that part of the gas. Let's go and take a look at this example here. It's got a gaseous mixture of 6.0 grams of AO2, 9.00 grams of CH4. It's placed into a 15-liter vessel at 0 degrees Celsius. What's the partial pressure of each gas, and what's the total pressure in this vessel? All right, so the assumption again is that we have a container here. It's got a bunch of gases, right? There's a bunch of little gas particles floating around. It's got another gas particle floating around of another gas. And the question again is, what's the partial pressure that the green gas and then the partial pressure of the blue gas that they contribute? And therefore, what's the total pressure overall? So effectively, our work's going to start off like this. The total pressure is what you're asking for, is equal to the pressure of O2 plus the pressure of CH4. Now, neither of the pressures are given to us, so we don't really have any numbers to plug in here, but we do have some other information. They give us a gram amount of O2, they give us a volume that is contained in, a temperature that is contained in. So from this, we can probably do a little work thinking about a gas, one gas, and we need to know some information about it. We can go ahead and probably apply ideal gas law. So for the 6 grams of O2, right, that one, you know that you can't plug that directly into the ideal gas law. But you do have R, you do have temperature, you do have volumes. You have to solve for P, right? Yeah, everything else is given. So you got that, you got that, you got that, you got that. Of course, the mole amount is not exactly given to you. You have to do conversion. So doing a little bit of just sort of quick math here. Some of you have to work it out, but assume that you can take care of this using ideal gas. 6.0 grams of O2, the resulting pressure that it contributes is 0.280 atmospheres of pressure. So the 6 grams of O2, apply the ideal gas law, and then you get 0.280 pressure or atmospheres of pressure. Do the same thing with our friend CH4. So let's try this out. It's 9.00 grams of methane, and the corresponding pressure there is 0.838 atmospheres of pressure. So now I have the pressure of O2, the pressure of CH4, and so the question is, what's the partial pressure of each gas? Well, the partial pressure of O2 is 0.280 atmospheres. The partial pressure of CH4 is 0.838. And so let's go ahead and finish the final answer, final question here. What's the total pressure? So the total pressure is equal to 0.280 atmospheres plus 0.838 atmospheres, and that should equal 1.118 atmospheres total. Now, this idea is fairly straightforward, but then we also can kind of influence or understand the relationship that pressure has with moles. There's a bit of a skip here that I'm going to sort of suggest that it's not something that we need to really derive and figure out. Just know that this is a relationship that can be shown if you want to do all the work for it. But we're not really going to do that. I just want to go and skip to the point. It says, in a mixture of gases, the mole fraction, so this is a new term here, the mole fraction is the ratio of number of moles of a given gas to the total number of moles in the mixture. Now, this effectively is kind of just a percentage almost. So if you see right here, the symbol is this x1, so it's kind of like a little bit scripted. I just do x's, x1, meaning x, the mole fraction of a certain gas, 1, is equal to the moles of that gas over the total moles of gas that are inside the container. Remember, this is talking about mixtures of gases, right? And so the mole fraction effectively is just the mole amount of gas 1 divided by moles of gas 1 plus gas 2 plus gas 3 plus however many gases are in there altogether. And that's the mole fraction represented with an x1. Notice that the mole fraction is presented as a decimal, not an actual fraction, or it's not a percentage. So for example, let's say you do some math and you have something that looks like 5 over 10, right? It shouldn't be 5 over 10. You'd actually need to write it as 0.5, right? So the mole fraction would just be 0.5. And if you wanted to, you can derive this, and this is the part that I was talking about. We're not going to do this necessarily, but you can apply the ideal gas law, and you can reach the following conclusion, where the mole fraction is also equivalent to the pressure of gas 1 over the total pressure. Now, that right there is a pretty nice relationship to have. Oh, by the way, you can rearrange it looking like this, but that's also a nice relationship you can have because, in a way, that's sort of the same relationship between moles and pressures. So effectively, if you have a pressure amount, then you also have if you have a pressure relationship, you also have a mole relationship, and vice versa. If you have a mole relationship, you have a pressure relationship. Now, I'm going to write this out, and this is something that I really dislike generally doing, which is going to be a little proportion, but effectively, this is what it is. Meaning that the relationship, the ratio of a mole amount to the total is equal to the pressure of pressure ratio of one thing to the total pressure. So it's kind of a nice relationship to have. So again, if you're not sure where this came from, remember that the x1, this right here, this is the link. These two are equal to each other, and you're substituting the n's and the p's. But overall, this is kind of a nice relationship to have. If you have the mole relationship, you also have the pressure relationship. Let's go see what this looks like. All right, the mole fraction of nitrogen in air is 0.7808. Calculate the partial pressure of N2 in air when the atmospheric pressure is 760 torr. All right, so let's try this out. The mole fraction of nitrogen, so X of nitrogen gas is equal to 0.7808. And they also want to know the partial pressure of N2. So the partial pressure of N2 is equal to the total pressure times the partial pressure of N2. All right, now, where did that come from? Again, it's rewriting what we had on the previous page here, right? This right here. The partial pressure of this gas is equal to the mole fraction of the gas times the total pressure, in which that's what we have right here. Partial pressure of N2 is equal to the total pressure times the mole fraction of N2. So let's put this together. We know that the total pressure, or the partial pressure of N2, I don't know, but the total pressure of atmosphere, or atmospheric pressure anyway, is 760 torr. And then you multiply that by the 0.7808 there from the mole fraction. And then you do a little bit of math and you get 593 torr. Example 2 here. The partial pressures of CH4 is 0.175 atmospheres, and that of O2 is 0.250 atmospheres in a mixture of these two gases. What is the mole fraction of each gas in the mixture? Well, if the mixture occupies a volume and so on and so forth, calculate total volume, and then calculate total mass inside this container. So this problem is going to have a couple of parts, obviously. So let's go and do what we can. First of all, what's the mole fraction of each gas in the mixture? Well, let's go and take a look. The mole fraction, right, that's going to be dependent on this X business. So we have X of CH4, and we also have the X of O2. There's the two things we're solving for. And if I want to get the mole fraction, it's easiest if I have the mole amount and divided by the total mole amount and so on and so forth. But unfortunately, I'm not given that at all for either of these gases. So let's do it instead using pressures. Now, if you remember from the earlier slide, it does have some relationship showing that the total pressure, the CH4, the partial pressure, that is, of CH4, and the total pressure, right, that's equal to the mole amount relationship too, right? So of course we're not given the CH4, so this is not really going to be a helpful relationship to work with. So I'm going to go ahead and cross that out. But do I have a partial pressure of CH4 and a total pressure? Absolutely, because I have pressures of that and pressure of that. So in fact, I can kind of do a little bit of work here. Instead of having to actually find mole amounts, I can just go ahead and use the pressures to help me figure that out. So what that's going to look like is going to be 0.175 atm over the sum, right? 0.175. I'm covering a space there, 175 plus 0.250 atm. And that's going to equal to 0.412. Let's try that better. 0.412. Then the mole fraction of O2, well, again, that's something you can plug in numbers here and figure out. So it's going to be 0.250 atm over the sum of the two, which is going to be 0.425 atm. That's going to equal to 0.588. Now, one thing I want to mention here is that I didn't even need to show that step, because really what I know is true about fractions is that the sum of all the parts of the fraction should equal 1. So ultimately, if I really wanted to, I could have done it like this too. Is equal to 1 minus 0.412, which is that mole fraction of CH4. And that would get me the same answer as 0.588. Part B, if the mixture occupies a volume of 10.5 liters at 65 degrees Celsius, calculate the total number of moles of gas in the mixture. Now, there's more than one way to approach this, and I'm just going to do this the most brute force way that I think is going to be probably the most likely way that you'll take it. But essentially, to figure out the mole of gas, we were given a volume, we're given a temperature. And from here, we might be able to figure out some work, right? Don't we have PV equals nRT, right? We do have pressure given to us from each gas. We have the volume of the container that they're in. The mole amount is that we're solving for. The R is always available, and temperature is given to us. So you can use PV equals nRT for each of those. But first, you want to do it for CH4, and then you want to do it for O2. An alternative way to do this, and this might be not as popular anyway, but instead of doing this in two different ways, what I can do at first is go ahead and say the total pressure is equal to, let's try this again. The total pressure is equal to the total mole amount times R times T. Right? So basically PV equals nRT. Instead of using these as individual gases, I can also do the same thing using the sum of pressures to get the total moles of gas, because ultimately that's not what they're asking for, right? They're asking for the total moles of gas, so that's what we're solving for. I can just stick that in there and be done. Now, you are recommended to try both ways, right? So try it the brute force way that we saw earlier, or you can try it the other way right here that I saw a minute ago, or I'm describing now, where you can just kind of add them up first and then do some work. Finally, calculate the total mass of the mixture. That's going to be something that I think you can figure out on your own. Okay, all right, that'll do it.